another remote talk, which will be presented by Danni Peng and will be for a paper entitled Learning an Adaptive Meta Model Generator for Incrementally Updating Recommender Systems. Hello, Danni. We can see you. We cannot hear you yet.
Okay, now can you hear me?
Yes, now we can hear you perfectly. Whenever you're ready, you can start.
Let me try the clicker. Okay, it works. Okay, can I start?
Yes, sure.
Hello?
Hello? Sure, you can start.
Okay. Hi everyone, I'm Danni Peng from Nanyang Technological University and Alibaba NTU Joint Research Institute. I'm honored to be here to present our paper, Learning an Adaptive Meta Model Generator for Incremental Recommender Systems. In real-world application of recommender systems, we have new data comes in every day. Therefore, it is important to periodically update the RecSys model in order to catch these trends, like the interest drift of user or term popularity, which will be making predictions in the near future. There are many strategies to update the RecSys model. One method is to update the model incrementally using only the newly arrived data. That means at each period, we restore the model from the last period and update the model using only current period's data. And as compared to methods that utilize larger window size or even the entire history, incremental update has the benefits of and sometimes better prediction performance when the However, there exists this problem of forgetting for RecSys incremental update. This occurs because the amount of training data from a single period is limited, while there might be just distribution drift across periods. And as a result, the model updated in this manner will overfit to the current period and fail to retain the long-term information obtained from the past training. Therefore, in order to achieve of better serving for the next period, we want to retain past knowledge that is especially useful for the next period's predictions. So to overcome the problem of forgetting, two lines of research have been developed. The first one is sample-based approach. This approach uses the past samples for current training by maintaining a reservoir of data. A key limitation of this approach is that the to be the informative or the forgotten ones, they can hardly represent the big picture of distribution. Instead, the model trained from the history can be seen as a better summarization of the past knowledge. Hence, another line of research termed model-based approach took advantages of this by extending the model. Some techniques include knowledge distillation or learning to combine past and present models. However, the existing methods for this approach suffer from a common limitation in that they only consider transfer between two consecutive periods, while the potential of creating the long-term information is overlooked. So before I introduce our proposed method, let's define the to update more formally. So given the current dataset dt and the previous model theta t minus 1, the current model theta t is obtained by minimizing the loss on the current dataset with the previous model as initialization. So without any post-processing, the updated model is directly deployed to serve for the next period. And as discussed before, this training strategy suffers from potential overfitting and forgetting issues. Hence, we introduce an adaptive sequential model generation, in short ASMG, and sequence of historical models to generate a better one for the next period serving. The motivation behind is that since the incremental model at each period is only trained on the data of that specific period, it can be seen as a very good representation of that period. So given a sequence of incrementally updated models, we are able to extract the temporal trends exist in this sequence, which may be very helpful for generating.
Sorry, can you hear me? Can you put the microphone, try to put the microphone a bit farther away because we hear some noise.
Okay, how about now? Better?
Yes, please try. Yeah, a bit closer. Okay.
How about?
That should be perfect. Thank you. Sorry for interrupting.
Okay. So given a sequence of incrementally updated we can now extract the temporal trends exist in this sequence, which may be very helpful in generating a better one for the next period. So to achieve this, we introduce a meta model generator denoted by MT for the T's period. So given a sequence of incrementally updated part 1 until theta t, we will generate the output model theta t star, which will be used for the next period serving by inputting this sequence of models into the meta generator. So the main problem is how to design and train the meta generator. We want to attain two desired properties for this meta generator. So firstly, we want it to have a good capability of modeling the dependencies exist in the sequence. So this can be achieved by a proper network design, which I will talk about in a few minutes. And the second property is the stable performance of producing a good model for the next period serving. And this is actually related to the optimization process. So to generate model that is particularly good at serving the next period, we need to ensure that the past knowledge that is especially useful for the next period serving is extracted. Therefore, we propose to update the parameters of the meta generator, omega t, by optimizing the output model towards the next period's data. And to ensure that the meta generator is sufficiently warm up before deploying online, we reserve some periods for the warm-up training. And during the online phase, we'll still need to update the meta generator in order to keep up with the changing sequential trends. Next, I will talk about the network design of the meta generator. So to capture the sequential patterns, we propose to employ GRUs for the meta generator design. So at each step, the hidden state is computed from the previous step hidden state and the current step input model, and the output model is obtained directly from the hidden state. And to improve the training efficiency and sequential modeling ability, we further propose two training strategies tailored to the GRU meta generator. So firstly, we noticed that the computation time of GRUs actually increases linearly with the sequence length. So to improve training efficiency while preserving the long-term memory, we propose to train the GRU meta generator on a fixed length sequence by continuing on a previously learned hidden state. So when training the meta generator, we take in a sequence of k most recent models as an input, and then use a previously learned hidden state as the initial hidden state. And to further ensure that more accurate sequential modeling, we propose the second strategy to train the meta generator on multiple periods data concurrently. So when training the meta generator, instead of optimizing the final step model towards the next period's data only, we optimize models at all steps towards the respective next data sets concurrently. And the objective now becomes a weighted sum of the losses at different steps. And then we use a linear decay function to compute the weights assigned to different steps. So to illustrate, the first strategy constrains the sequence to have fixed length and reuses the hidden state learned from the previous training as the initial hidden state for the current training. And the second strategy strengthens the sequential patterns learned by concurrently optimizing the output models at different steps. And to test the effectiveness of the proposed model updating method, we instantiated on this embedding and MLP-based model, which is a general deep learning-based RecSys model. This model mainly comprises the embedding layers that transform the sparse features into dense vectors and MLP layers that learn the interaction amongst the features. And next, I will talk about our experiment. So we conduct experiments on 3 public datasets and 1 industrial dataset from Lazada. And we compare our methods against several model update strategies, including the conventional incremental update, the batch update with larger window size, and the state-of-the-art sample-based and model-based approaches, and as well as an alternative meta generator design with a linear combination function. So the results here are averaged over 7 test periods. from results, we can draw some conclusions like the performance drops for batch or incremental update as the window size increases. And the model-based approach actually performs better than the sample-based approach. And the GRU meta-generator design is better than linear counterpart in terms of modeling the sequential patterns. And we also plot the performance at each test period. And this blue line is our proposed method. So we can see that it consistently outperforms the baselines for every test period. And furthermore, we introduced some variants for the ablation study. And from the results, we see that all the designs actually contribute to the performance gain. And yes, finally, we conduct sensitivity analysis to test the effect of input sequence length and GRU hidden size. And we observe that the optimal sequence length is around 3 to 4 periods, and the optimal hidden size is 4 units. Yeah, to conclude, we propose an ASMG framework to generate a better serving model by encoding a sequence of historical models. And we introduce a GRU-based meta-generator capable of capturing the sequential patterns. And we further develop two training strategies to improve the computational efficiency and sequential modeling ability of this GRU meta-generator. And last but not least, we conduct extensive experiments on 4 datasets to test the effectiveness of our proposed model updating method. And with that, I will end my presentation. And yeah, thank you.
Thank you, Danni. Okay, is there any question coming from the audience? Not yet. So, Danni, for you, the same question as the previous speaker. Fernando is asking if you're planning to make the source code available.
Yes, the source code is online. I open source it like when 2 months ago. Yeah, you can.
Okay.
Yeah, you can check our paper.
Okay, so the paper has the link. Okay, thank you.
Yes.
Any question from the audience? Not yet. I don't see a question online, so I will ask you one question. I've seen that the industrial data set was behaving quite differently from the public ones. Sometimes it had the best results, sometimes the worst. And I was wondering if you had any insight, I don't know, maybe the type of interactions were different. Was there any difference from the data set that we all know and from the industrial data set that you used?
Okay, so the industrial data set is actually an e-commerce data set. And then the difference is that for Lazada, the period is, the updating period is actually 1 day per period. So but for the benchmark data set like Movie Lens, it's like around 2 to 3 months per period. So for e-commerce, it's like more frequently update. So for this kind of data set, of course, it's necessary to update the model daily because in order to capture the most recent user interest. But for this kind of scenario, our meta model generator will actually capture a shorter cyclic trends, like what are the temporal trends across a week? Like for example, like during weekdays, what kind of stuff people might be interested in, and during the weekends, the interest might be different. So depending on the duration of the period, our model will capture different kinds of temporal trends. Yes.
Okay, thank you. Okay, I see that at the moment there are no more questions, but I invite you to interact with the speaker and the authors in the hub. And please, let's thank our speakers again. Thank you, Danni.